Hello, my name is Gemmi and I am a master student of the University of Trento. In this presentation I'm going to talk about the work on wireless network topology generator I have done together with Professor Leonardo Maccari from the University of Venice. The outline of the presentation is the following, and we'll analyze the existing topology generators such as TrueNets and NPART. Then we're gonna explain and show our improvement on top of NPART called NPART Plus and its evaluation methodology, and finally we'll show the results and give some conclusions. So the research field we deal with is the use of topology generators to model realistic multi-hop wireless networks, which are gaining attention in the last few years. Think about 5G wireless mesh backhauling, for instance. The goal of this presentation is to compare state-of-the-art topology generators with realistic topologies and to improve the accuracy of existing topology generator called NPART. In literature we can find a large number of topology generators, but most of the time when we talk about wireless mesh networks, researchers either use classical generators like the Erdős-Rényi or the Barabasi-Albert, which are well known and studied, or they use generators modeled specifically for and onto wireless mesh networks. In this case, the most used one are the Serda-Alamberne and the Milic-Malek, also called NPART, which have been both modeled onto the topologies of real networks, Givinet in the first case and Freifunk in the second. Here we focus on NPART, that approaches the problem of topology generation with a mixed geometrical and stochastical approach. In fact, it generates topologies that lies on a Cartesian plane by placing nodes in random position and connecting the vertices by respecting a degree distribution that has been given as a parameter. These allow it to generate topologies that both preserve realism and have a sufficient degree of randomness. However, it needs as an input parameter the degree distribution, which is provided by the analysis of some specific wireless community network. Since most wireless community networks are developed in urban areas, it's hard to find these data from non-urban wireless community network, and thus it's difficult to reproduce and generate topologies from these other areas. An additional issue is related to the fact that like most wireless network generator, it doesn't have an abstraction model, and for this reason it can take into account the correlated shadowing. A novel approach to generate realistic topologies have been proposed with TrueNets. This tool works by emulating the growth of a wireless community network in a specific area for which the morphological data and the building shape are available. In this figure we can see the morphological data as in the picture above as a leader dataset, and the building shapes obtained by OpenStreetMap in the picture below. TrueNets generates topologies of networks that could actually exist, and this approach is totally based on open data, and the source code of the emulator has been released as open source. Two main issues with this approach are related to the fact that these datasets are not widely available, and sometimes they require handwork to harmonize them. Moreover, the generation of these networks takes a long time, and for instance the generation of a network of 500 nodes can take up to 1 hour of computation. For the evaluation of the wireless links, first TrueNets check whether there is line of sight between the nodes, and then it approximates the path loss by using the free space path loss plus the knife edge approximation for the two highest obstacles that enter the Fresnel zone. The emulation process starts from a seed building chosen by the user, and then at each iteration it extracts a random building in a given radius around the network and tries to connect it to the network. When it reaches a size of 500 nodes, the process stops and the topology is saved. We introduce NPART Plus, a merge of NPART with TrueNets, retaining the simplicity of the first and the realism of the latter. We plugged the average degree distribution extracted from TrueNets topologies into NPART, and in this way we overcome the lack of realistic degree distribution from topologies of wireless mesh networks in non-urban areas. We also enforced a given edge-to-vertex ratio measured on the topologies generated by TrueNets in order to achieve a higher accuracy. We generate 55 topologies from each area: urban, suburban, intermediate, and rural. And then we aggregated these topologies together and we extracted the average empirical degree distribution and the average edge-to-vertex ratio. We plugged these two parameters into NPART+ and we have generated 110 synthetic topologies. Finally, we calculated various graph analysis metrics and we aggregated them for each area. In all the figures, we compare the metrics in different areas, which you can see on the x-axis, and the metrics from different generators, which are identified by colors. We have TrueNets in red, which we take as a ground truth. Then we have NPART in blue and NPART with leaf pruning in green, which is a variation proposed by the original authors. We have then NPART+ in orange and NPART+ with edge pruning in yellow, which is a variation that we have proposed. In this specific figure, we can see the articulation point density metric. An articulation point is a node that, when is removed by the network, it partitions the network into two disjoint graphs. And this figure shows that generally all the networks generated by the generators have a higher degree of articulation point. However, NPART+ with the edge pruning shows a significant improvement with respect to the original NPART, as the metric value is close to the one of TrueNets. It also shows a significant difference from one area to another. These other metric shows in the figure is the size of the largest beconnected component, that is the largest subgraph without an articulation point. From this one we can observe two main results. The first one is that networks outside of urban areas tends to have much smaller beconnected components, presumably due to the smaller number of obstacles between the buildings. And the second result is that NPART+ is the generator that better approximates the networks outside of the urban area, which was one of the goals of that this research was trying to find. The average clustering coefficient is a metric that tells how dense a graph is locally, and these figures highlight two relevant results. The first one is that there is a strong difference between graphs generated in different areas in terms of clustering, and the second one is that all the generators fails to approximate correctly this property. And presumably the latter is due to the fact of the absence of correlated shadowing in the generators, and in fact it is emphasized in urban areas where the obstacles are more dense. The average shortest path visible in the graph shows another main difference between topology generator and the real network they're based on. In fact, also here the absence of shadowing model tends to allow the generation of much longer links and thus a smaller average shortest path. Also in this figure we can see some improvement brought by NPART+ with edge pruning, but these are not sufficient to approximate correctly the value of the original topologies. These figures and the next one shows the derived robustness metric, which describes the resistance to the network to an increasing number of random failures among the nodes. By measuring the size of the largest component after each potential failure, we evaluate this robustness, and a higher metric means a higher robustness of the topology. From these results, we can observe how all topology generators tend to overestimate the resistance of the network, creating networks that presumably, due to longer links and the lack of correlated shadowings, are more resistant. Also here we can see how NPART+ with edge pruning is the approach that better resembles and approximates the ground truth and TrueNets. This other figure shows the resistance to the network to targeted attack. In this case, the sequence of failing node is not random, but is chosen to maximize the damage. Here we can see how the results is the inverse with respect to the random failures. In fact, here TrueNets tends to create networks that are less susceptible to targeted attack. Another interesting result is that here, unlike any other metric, NPART+ outperform NPART with edge pruning in accuracy with respect to the ground truth. In conclusion, we have shown that state-of-the-art topology generators are mostly suited for urban environments and represent poorly rural and suburban areas. Moreover, we have shown that topologies from these areas have a substantial difference among them, and these highlight the need of generators tied for these areas. We've also shown that existing generators, specifically NPART, can be improved with data from TrueNets, but the lack of abstraction models in stochastical generators and thus the lack of a correlated shadowing doesn't allow the generators of topologies to be accurate enough to represent the clustering coefficient, the path length, and robustness properties of the original networks. Thank you for your attention, and I hope you have enjoyed the presentation. If you have any doubt, we will be available at the organized question and answer session. Thanks. Goodbye.